The poster title is Efficient Distance Sensitivity Oracles for Real-World Graph Data. My name is Jong-Yul Lee, and this is a joint work with Professor Chinan Chung. In this paper, basically, we consider recoverable network failures. For example, in road networks, a car accident can be considered as a recoverable failure because it may cause heavy traffic congestion and it will be eventually cleared up. Computing a point-to-point short-distance query with such network failures is called the distance sensitivity problem. In order to solve this problem, one can consider to use a traditional online shortest path algorithm like DISO algorithm or a fully dynamic algorithm. Since the DISO algorithm does not have any index structure, it guarantees stable performance. However, as we know, it is way too slow. The fully dynamic algorithm also has a problem with this setting because it should update the index structure due to the failures so that it should store queries during the update time. This problem may lead to very slow latency. Therefore, in order to achieve fast latency despite such failure occurrence, we need efficient algorithms answering a query without any storing. Given a directed graph G, the distance sensitivity problem is to answer a query Q, which is represented by a tuple STF, where S is the start node, T is the destination node, and F is a set of n-most F failed edges. The query asks to compute the shortest distance from S to T in the graph excluding the failed edges in F. An algorithm including a certain data structure for this query is called a distance sensitivity oracle. For explanation, here are our representation for our path and a distance. Then, for this problem, there are two naive solutions. The first one is an online shortest path algorithm like the DISO algorithm. The other is storing the answers of all possible queries. However, it is not practical. Let's explain our first work named DISO, which means a distance graph-based oracle. DISO is a variant of transnode routing, which is a famous shortest routing framework. This framework is based on an assumption that if we carefully choose some special nodes, we can make most shortest paths with many hops pass through at least one of them. Such nodes are called transit nodes, and the shortest paths between transit nodes are supposed to act like highways. In order to explain this idea, let's introduce two cases with the shortest path from node S to node T and some transit nodes. The first case is that the shortest path includes transit node U and V. In this figure, a curved line represents a path and non-black nodes are transit nodes. Then suppose that there are transit nodes within a few hops from S, and most shortest paths from S contain at least one of the transit nodes. Since they are close from S, the cost for computing shortest distances from S to them must be cheap. Also consider that there are similar transit nodes for node T in the reverse direction. In this case, if we can efficiently get the distances between transit nodes with a kind of distance table, the shortest distance from S to T can be easily computed. The other case is that the shortest path does not include any transit node. We hope that the length of this shortest path is likely to be short, so the cost for computing the distance, even with an online shortest path algorithm, wouldn't be expensive. This is the basic principle of TNR. This principle has expressed by following two steps. The first step is that if PST does not have any transit node, we directly compute the distance by an online shortest path algorithm. Otherwise, we first find access node from S and T. A transit node is called an access node from S if there is a path from S to that node which does not include any other transit node. The access node for T are similarly defined, but in the reverse direction. And one can ask about how to determine the condition of the first step. We will explain that later. The second step is that we compute the minimum distance among passes derived with S, T, and the access nodes. The minimum distance can be expressed in this formula. Note that P hat xy is the shortest path from x to y without any intermediate transit node. D hat xy is the distance of P hat xy. In this expression, dt in the middle term stands for distance table. So dt uv is the shortest distance from u to v, and it is stored in the distance table. Since usually the number of all transit nodes is small, the distance table is acceptable for storing failure-free shortest distances. Since we know the distance information with S, T, and DXS nodes, TNR can efficiently find a pair of transit nodes, achieving the minimum distance from S to T. Let's explain how to adapt TNR for our first oracle. First, given a query, since D hat SU and D hat VT are distances from XS nodes, they are computed by a modified version of the extra algorithm in the graph, excluding the failed edges. The modified version is designed to avoid the neighbors of a transit node, so that the paths found by this algorithm do not contain any intermediate transit node. Let's create the bounded Dijkstra algorithm. Next, we can't accept the distance table because the number of possible edge failures is so huge. Instead, we propose a way of computing the shortest distance from U to V on an overlay graph called the distance graph. The distance graph consists of transit nodes. For any two nodes, x and y, in the distance graph, if there is a path from x to y which does not include any other transit node in the input graph, then the edge between them is included in the distance graph. You can see such a path from x to y in this example. Note that the edge from x to y in the distance graph has a weight, which is the distance of the shortest path from x to y in the input graph, avoiding any other transit node. This weight can be computed by the bounded Dijkstra algorithm. In this figure, the green nodes are excess nodes from S, the yellow nodes are excess nodes to T. Since we know the distances from S to its excess nodes, and the distances from T's excess nodes to T, we can compute the distance from S to T with this distance graph. The query algorithm of DISO is a Dijkstra-like algorithm, and it works based on this idea. The remaining thing for the query algorithm is how to handle the case that the edge xy will be relaxed in the distance graph, but its corresponding path in the input graph contains a failed edge. In order to detect such a case, we construct path tree of x in preprocessing, which consists of shortest passes from x computed by the bounded Dijkstra algorithm. Note that those shortest paths do not contain transit node as an intermediate node. Therefore, once failures are detected with the path tree, then we say that x is affected by the failures. In that case, some of the edge weights from x may be invalid. Their corresponding paths in the input graph can have failed edges. Since exactly identifying which edge weights are invalid requires somewhat expensive cost, we recompute all the edge weights from x based on the path tree of x. After the recomputation, the algorithm conducts relaxation with new edge weights. Now we can explain how to determine the shortest path from S to T has some transit nodes or not. Since we run the bounded Dijkstra algorithm from S, if the result shortest path from S to T doesn't contain any transit node, the answer is the same as the distance reported by the bounded Dijkstra algorithm. That is, instead of computing something in order to determine case 1 or case 2, we directly compare with the distances from two cases. Since the distance graph is uniquely identified by a transit node set, transit node selection is very important for our Aura case. Our transit node set selection strategy is to utilize the k-path curve. For some integer k, our k-path curve C is a set of nodes such that all simple passes consisting of k nodes in the input graph G pass through and is one of the nodes in C. Simply, we want to use the nodes in C as transit node. The decent property of the k-path cover is that The length of passes which do not contain an intermediate transit node is bounded by k. This length bound is used to manipulate the cost for running the bounded X algorithm and the edge weight recomputation. Let's introduce our second oracle. This oracle is an improved version of our first oracle based on the A-star search heuristics. The A-star search algorithm is very similar to the Dijkstra algorithm, but its objective function includes a heuristic estimation of the distance to the destination node. It is well-known fact that for correctness, the heuristic estimation should be a lower bound of the actual distance. If we have such a heuristic function h, since DUT is lower than or equal to DUTF, h is still admissible for the distance sensitivity problem. We use a heuristic function proposed by Goldberg et al. In 2005, which is based on landmarks and triangle inequality. This heuristic function is still accurate, even if it's used under the distance sensitivity problem. Finally, we propose two boosting techniques for our oracles. For this purpose, we introduce a kind of distance graph H of the distance graph D. The partial detouring consists of two steps. At the first step, a path P init from S to T is computed by a modified version of the second oracle. This modified version works with an assumption that there is no affected transit node. For efficiency, the modified version also utilizes the edges in the distance graph H for finding. Then the second step finds a detour of each subpath xy over the path P init if x is affected. For example, if U and HI are affected, then the algorithm recomputes the distance from U to HI and the distance from HI to HJ with the second oracle. In this way, we can successfully reduce the search space to compute a whole solution path. The next boosting technique is distance graph specification. This technique works with a guarantee of alternative path existence. For example, suppose that we want to remove an edge xy, which is on the shortest path from U to V. If we can guarantee that there is another path from X to Y having distance lower than beta W, then the distance from U to V is changed, but it is bounded by beta times the original distance. This idea is easily extended to the case of removing multiple edges. However, it cannot guarantee the better approximation with failed edges. Nevertheless, it practically works. In order to demonstrate the performance of our oracles, we compare our oracles with some competitors. The A-star search algorithm, a recent fully dynamic distance oracle, and the Dijkstra algorithm. We compare them in terms of query time over the number of failed edges. Note that for each query STF, S and T are randomly selected. From the empty failed edges set, each failed edge is randomly selected among the edges on the current shortest path and added into the failed edges set. The comparing result over those failed edges is presented here. As we can see, in node network, our oracle, named ADISO, is faster than any other algorithm. ADISO with P is our second oracle with partial detouring. We can see that partial detouring successfully accelerates the query performance of the second oracle. In the result with social network, the A-star search heuristic is not well effective. Instead, DISO with the specified distance graph is much faster than any other algorithm. In conclusion, we propose two efficient distance sensitivity oracles. We also propose two boosting techniques with slight loss of accuracy. In the full paper, we propose update algorithm for our oracles to handle permanent network updates. In the experiments, our oracles are much more efficient than any other competitors in terms of query performance. The boosting techniques are also effectively helpful to improve our oracle's query performance. To the best of our knowledge, this work is the first practical work dealing with the distance sensitivity problem with real-world scale networks. Thank you.